So welcome to this month's invited talk of our ICG Lab Talk series, first talk in the semester, this new semester. It's my pleasure to welcome Dmitriy Shutin. He is working at the German Aerospace Center in Oberpfaffenhofen. He did his PhD at TU Graz, where he was also a teaching assistant and assistant professor before he moved to Princeton University to be a research associate. And now he moved in 2011 to the German Aerospace Center, where he leads the swarm exploration group. And we're looking forward for a talk on physics-assisted multi-robot exploration and spatial temporal dispersal phenomena. It's related to our research, our drone-based research. We are actually working on a joint DFG FAF proposal, and I'm very much looking forward to your talk, Dmitriy. It's yours now.
Yeah, thank you, Oliver. Thank you for kind introduction. So let me start with the talk. So as you have heard, I'm with the German Aerospace Center now. So DLR, or German Aerospace Center, is actually a pretty large organization. We're about 10,000 employees and have around 55 institutes scattered through Germany. So it's we're not located in one place. And although German Aerospace Center has letters L and R, so Luftraum and Raumfahrt, in its title, we are concerned not only with aeronautics and space, but also with transportation, energy, security and digitalization. So there is actually a pretty broad spectrum of activities that DLR covers. And it also has a number of offices in Brussels, Paris, Tokyo, and Washington. So we are a pretty big organization with, I would say, very wide interest in technology and research. The center where I am located is in south of Germany, close to Munich. It's a research site close to the Oberpfaffenhofen. It's one of the largest research sites in DLR, in Germany also in particular. And there are several research institutes, for example, my institute, Communication Navigation, Microwaves and Radar Institute as well, Remote Sensing, Atmospherics Physics, Robotics and Mechatronics Center, as well as System Dynamics and Control, as well as a number of technical facilities. So as you can see here on the map, we are located relatively close to a small airport where also some of the experiments are done. We also have 2 aircrafts that are used in multiple experiments at DLR. And our building is actually close to the main site. We have grown over the years recently and have actually left the DLR site and allocated close to it. As I said, we have grown, so I'm not going into the details about the institute. Just to mention that in addition to, for example, swarm exploration, there are also a lot of activities related to satellite communication networks, development of satellite navigational system, Galileo system, GPS, also navigation for nautical systems. We have institutes not only here in South Germany, close to the Oberpfaffenhofen, but there is also one institute located in the north, close to the Berlin, in Neustrelitz. They're dealing with navigation system for ships. So the spectrum is relatively bright. So we cover in our institute work basically all aspects that are considered in DLR, maybe with an exception of the energy. So space, aeronautics, transportation, security, and digitalization. So these are the topics that are addressed at different groups in the institute. Of course, what my group is doing, and particularly what my department is doing, is mainly related to space and transportation. So there are lots of work related to development of transportation systems, navigation system for Earth as well as for space. And swarms are in particular those topics that I would say are very much space related. So we develop concepts and technologies for enabling planetary exploration using multi-agent systems, swarms in particular, which communicate, exchange data, and analyze sensor data. And the later, the analysis of the sensor data is actually the kind of the focus of the talks that I will give today. So physics-assisted multi-robot exploration of spatio-temporal dispersal phenomena. So what is this? So there are kind of a few key words that sounds very scientific, but in general, what we want to do is quite simple. So we want to use robots to locate an unknown number of sources that produce gas or some material that emanates from the sources. The robots, I would say, have sensors that are able to perceive these gases. So they typically measure concentration of the gas at different locations. And our objective is, based on those individual measurements performed at different locations by the robots, determine where the sources are, how many sources we have, map the individual concentration, sorry, not individual concentration, but rather distribution of the gas over the territory. So that's one big goal. And the second one is devise a strategy for the robots to move to sampling locations that are optimal in some respect. So we not only want to estimate the parameters of the process, but we also want to guide the robots to navigate them towards interesting, important locations of interest. Of course, what you see here would probably be very much interesting for applications on Earth, but at the same time, I would say the methods that we develop here, as you will see, actually find applications not only for gas localization, but could also be used for exploration of icy moons. So as you might know, for example, Enceladus, a moon of Saturn, is an icy moon that has a liquid ocean beneath the icy surface, where there is a possibility of life. And of course, this is not something where we will be able to have a tele-operated drone or submersible robot that can explore it. So we need an autonomy. So the robots need to be able to take autonomous decisions, select optimal sampling positions, so that they can, for example, locate such sources like, for example, this black smoker. So the thermal sources, which on Earth, as we know, give rich environment for life, even under conditions where typically we would not expect living organisms. But also, for example, underwater pipeline inspection is very interesting application. So instead of doing it that using humans who have to go underwater and inspect those pipelines, we can use autonomous systems that can smell essentially material in the water and understand its dynamics, and in this way autonomously locate, for example, broken places or leaks from this infrastructure underwater. How do we solve this problem in general? So what is the general approach to solving this problem? As a scientist, we typically start with measurements and the process model. So that's the first step that we typically take when addressing any kind of exploration problem at hand. So we analyze what kind of data we can gather, what kind of sensor equipment we have, and then we look what are the models that scientists have developed to represent the processes of interest. As you might know, when we have models and we combine them with the measurements, essentially the process is known as data fit, as model fitting. This is exactly what we do as the first step. So we try to see how this combination of the modeling and the measurement data, or this model fitting, can be implemented in a cooperative inference fashion or in a cooperative form. Why we want to have it cooperative? Because we don't have a single robot, we have multiple ones. We want to exploit the possibilities that our system can carry multiple computing units. So we want to actually, from the local measurements that are collected by individual units in the swarm, come up with a cooperative global representation of the environment. Because this is global representation is something which we hope will allow us to drive the whole swarm to optimal sampling location. And although one can design, there exist actually quite different approaches to the exploration and to the navigation. In this respect, the methodologies that we follow is sometimes referred to as infotaxes. So essentially, we use our models to quantify a spatial information distribution that is contained in our measurement data or in our estimated parameters, which is actually quite closely related to uncertainty quantification. And this parameters, this infotaxes approach, we use to define what are the next measurement positions for the swarm. These measurement points should ideally be selected such as to provide most information about the process of interest. This is where the drones are then navigated. And at those measurement positions, new measurements are taken, and essentially the whole loop is repeated several times. So we go from measurement data to cooperative inference. The cooperative inference provide a basis for computing the uncertainty on information distribution in space. These give us essentially a cost function for selecting optimal measurement location, which gives us new measurements, and the whole cycle is repeated. And as we can see, one can essentially identify two key blocks that I will also try to address in this talk. So the first block is clearly inference and modeling. So it essentially addresses, given a swarm of robots able to take measurements, how do we perform inference in a cooperative fashion? That's one aspect. And the second aspect is, given this estimated model, how do we explore and how do we navigate using this learned information? So these are kind of two blocks that are essential to the approach that we promote. And in what will follow, I will try to focus on these aspects and explain how we implemented these systems. So let us begin with problem modeling. So as I said, we are dealing with exploration of gas, and here we actually instead of, let's say, inventing a wheel, we turn to the physics that explains us how the gas actually moves in space. If we think about the gas diffusion or the propagation in space, then essentially there are three quantities of interest that we're interested in. The first one is, of course, concentration of the gas. So it's a spatial function, which is of course depends on time. So that's a function f here, and it represents the spatial change, or essentially spatial concentration value of the quantity of interest. Another one is the concentration source. Sorry, it's other sources. So it's a small typo. So it's a source distribution, which actually drives the process itself. And of course, advection or the wind, that essentially a main mechanism that is responsible for distribution of a gas in space. And all these quantities, all these functions are essentially functions of both space and time. And the physics of it is, or the relationship between those three quantities is captured by so-called advection diffusion equation, which describes the functional change of the quantity of the concentration in time, subject to this term, the first term, which is a diffusion. So it tells actually how the gas propagates just due to the Brownian motion of the material or the molecules in the material, and how it changes due to the wind. So this is an advection term. The right-hand side of the equation typically is a driving force, or essentially is a source function that produces this distribution. Clearly, none of these functions are measured directly. It is actually our measurement system, so our robotic system or swarm, that can observe these quantities indirectly. And therefore, as a part of our, in addition to our process model, we also have a measurement model which relates how these quantities are related to the sensors that we use on the drones. Typically, or the systems that we use right now is able to measure both the gas concentration. So we are able to take a sample concentration value, of course, subject to a certain amount of noise. And we are also able to measure the wind. So we can measure the direction and speed of the wind at a particular location, again, subject to a certain random perturbation. So how do we actually approach such models? So how do we deal with these models? So mathematicians typically begin with a discretization of those equations. So unfortunately, in rare cases, these equations can be solved analytically. So most often we require numerical tools. And as you can imagine, the first step into developing numerical tools is the discretization. So we need to go from essentially from a continuum in both space and time to a certain finite dimensional space, to discretization. And in this case, we follow more or less a standard approach that is used for the analysis of partial differential equations. At the first step that is typically done, we go from a so-called strong version of a partial differential equation that you saw before. So the model, the original model, is also called a strong version, to so-called a weak form, which essentially redefines the equation with respect to a certain test function phi. So you can think of it as a kind of an inner product between your equation and some test function phi that you need to select. So that would be the first step. And the second step, we use a so-called Galerkin method. So it's essentially a classical approach to discretization of this partial differential equation. And the method consists of defining a certain set of fixed spatial functions psi. So these functions are fixed. And all functions of interest, for example, the concentration distribution, is then represented as a series expansion. So that's what you see here. So you approximate it as a series expansion of this fixed basis function psi I, where the expansion coefficients phi sub I are essentially the coefficients that are unknown. So these coefficients, these expansion coefficients, will represent the coefficients of interest that we will then eventually estimate. The psi functions are fixed, and this basis expansion is used then for all functions of interest. So for concentration measurements, for source signal representation, for test function representation, as well as for the wind. So we come up with these series expansions, and typically what we do, the first step that we need to do is, of course, we need to define these basis functions, and they're generally known as finite elements. So we effectively discretize our space, if you will, into these triangles. You can also define other finite elements for this purpose, but this is a fixed representation. So this is how the space is represented in this set of these discrete triangles. And the vectors of interest for us are, of course, the coefficients of the expansions for the respective functions. And these discrete representations are then plugged into our weak form formulation. So I will just shortly outline kind of the basic steps. So we just plug in this discrete finite dimensional representation into our equation. We do some math. And at the end of the day, what we see is that our representation or our weak formulation of our equation can be represented as a function of our expansion coefficients here, which are functions of time, and fixed matrices, which are essentially functions of our finite elements or space discretizations. And we can do that for all terms in our equations. For source term, we can do that also for time derivative term, and we would find a similar representation. We would do that for the diffusion term, as well as for advection term. So we would do that for all the elements in our equation, and we would realize that essentially it's just a combination of inner products with a certain certainly computed matrices, which are functions of this finite element space that we have created. And after doing all these steps, at the end of the day, we arrive to a finite discrete space continuous time equation, which essentially an equivalent, a discrete space equivalent of our diffusion equation, where the expansion coefficients in our discrete representation are now the unknown functions. Clearly, the next step would be also discretization in time, and that gives us the final discrete time, discrete space representation of our PD. So that's this is how we bring this time continuous space-time dynamics into a discrete world, which we can now implement on a computer. As a small addition to this equation, we typically also need to define boundary conditions. As you might know, for partial differential equations, we need to specify boundary conditions to ensure that equations are well defined. So that's concerning the model itself. So what about the measurement equation? Well, here, essentially the measurements, we assume that the measurements are linear. So typically each sensor has a certain measurement characteristic or point spread function. And the measurement is essentially a convolution between the point spread function and the process itself, depending on what kind of sensor we use and what kind of or how the measurements are performed. These equations might vary. In our work, we used might be slightly simplified representation. So we assumed an in situ sensor. So the robot is able to drive into the gas plume and take a point-wise concentration measurement of the gas. Similarly, for the wind, we assume that some of the robots are equipped with anemometers, so we are able to measure wind in 2 or in 3 directions. Again, this is a point-wise measurement. Both measurements are corrupted by noise, so it's a relatively straightforward measurement model. All right, so now we have our discrete representation of the equation. We have our measurement model. How do we perform inference? And this is essentially one of the particular aspects of our work. So instead of doing classical numerics or numerical analysis of partial differential equation, as it is typically done, we actually take a probabilistic approach towards solution of these equations. The probabilistic approach has a number of advantages. First of all, we can hide some of the model mismatches into the variances of our prior distribution or derived distributions. And second, this probabilistic inference will be actually crucial for the exploration step because it will provide information about the parameters of interest and it's their spatial distribution. So that's that will be an important step for the exploration, as we will see later. So how the probabilistic inference is formulated? Well, the first thing that we do, we start, we relax a little bit our gas model. So our model, we say it doesn't have to hold exactly. So instead of saying that it is the equations, the left-hand side of the equation has to equate to 0, we say, well, it's actually some residual signal R that we assume to be random with 0 mean and a certain precision tau sub s. So this allows us to effectively formulate the probability of the concentration value given the wind and the sources. So given the information about the sources and the wind distribution, we can now calculate the probability of the concentration by assuming that this residual signal follows a normal distribution. In a similar fashion, we look at the measurement model. So again, here we assume that the perturbation of our concentration measurement and the wind measurement are Gaussian, that effectively allow us to formulate the likelihood of the parameters of interest, so wind and concentration, given the measurement as Gaussian densities. So you see that we are going actually in it's more or less a classical approach to representing the likelihood and a price in our model. And of course, our prime goal is to understand or estimate the source distribution functions, the concentration, and the wind, given the measurements that we have collected by our swarm. So the Bayesian inference would tell us, well, what we need is a posterior over the parameters of interest given our measurements. And if we look what this posterior contains, is that essentially it contains a likelihood function, which is given by our measurement equation. It contains our now relaxed partial differential equation model that relates wind and sources to the concentration values through the equation. But of course, we need to define the prior distribution because we are following the Bayesian approach. We need to assume something about the wind and about the source. So concerning the wind, at first we follow a relatively conservative approach. So first of all, we say, well, there is no distinction between turbulent and laminar components. So we say it's a relatively smooth process. We had not taken into account the turbulences in the wind. We also assume that the X and Y directions of the wind in Cartesian coordinates are independent. So it's a simplifying assumption. It saves us a little bit of a gray hair during the inference and actually numerical implementation of the method. We relax this assumption later, and we'll come to that at the end of the talk. But at first, we say it's relatively simple assumption about the wind. So it's both X and Y directions of the wind we assume to be normal with a certain nominal direction or certain mean and certain variance in X and Y directions. And those have to be fixed. So these remain as a set of parameters, feed parameters in the system. They can be taken, for example, from weather forecast. So that's, again, it's a prior information. So that's information about the wind that we obtain before any measurements are done. Concerning the sources, so here care has to be taken because, as I mentioned in the beginning, the sources are essentially unknown. So we do not know neither their number nor their spatial location. And the question is here, how do we approach modeling of the sources in this case? And the approach that we follow here is based on so-called sparse Bayesian learning. So essentially we assume that there are a few distinct gas sources. We do not say how many. We say that in this discrete representation, so these expansion coefficients, if you remember, so we say that the sources are, the elements in this vector are basically zero at certain locations, and at certain locations they're non-zero, and those that are non-zero are actually the sources. And we want to find this vector U such that, or the source distribution, such that there are a lot of zeros and only the locations that are non-zero represent the sources. So effectively we say that the vector U, the source vector, has to be sparse. And we want to find such a sparse vector as a result of our optimization. And the approach as we follow implies that we need to constrain the prior about the sources. And the sparse Bayesian learning is a mechanism that allows us to enforce the sparsity constraint on the unknown vector by effectively introducing additional hyperparameters and making sure that our source prior, so the prior over the source distribution, is actually a combination of the two. One is a source given the hyperparameters times the prior over those essentially a hyperprior, again parameterized in a certain way. And such formulation is known as a hyperprior formula or hierarchical prior formulation, or Gaussian scale mixture prior, because it includes two terms. So the first term, which is a Gaussian prior over our source values, And a parameter of this prior is a precision. So that's this gamma I sub I here is a hyperparameter that controls the width of the prior. So you can think of this as follows. So if gamma is infinite, then essentially our prior assumption about our source is zero mean with a zero variance. So we say our source is essentially the value of the source, in this case is zero. And if gamma is not infinity, smaller than infinity, then we have a source with a prior that is zero at the center, but with a variance that is larger than zero. And in this way, through this hierarchy, we are essentially able to infer that an effective prior that we put on our sources looks like or is actually student t distribution. So if you look at the contour plot of the student t distribution, you would see that most of the probability mass is kind of spread out through the axis. And the hope is that that when we'll combine this prior with the likelihood, we will find a solution somewhere on the axis in our parameter space. So our solution will be sparse. Of course, the price that we pay, we have more parameters. So we now also need to estimate the hyperparameters in addition to all the unknown variables that we have. But yeah, that's a prior. Sorry, that's a price that we need to pay. But at the same time, the analysis of this prior actually shows that most of the steps can be analytically tractable. So as you can see here, this Gaussian scale mixture with those selected hyperparameters, or the hyperprior selected in this way, forms a so-called conjugate prior form, which allow us to analytically find values of the posteriors in this case. So that's it makes a problem analytically tractable. So let us see what is the effect of the sparse Bayesian learning if we would use such a prior. So on a very simple example. So here we have a measurement model which has two unknowns, U1 and U2, and just a single measurement. So we measure Y equal to 1. And the idea is having this model likelihood estimate parameters U1 and U2. Clearly, we cannot do this with a single measurement. We have two unknowns, only one measurement. So we need to introduce a certain regularization. So classical approach, also known as a Tikhonov regularization, would assume that we are looking for essentially the smallest L2 norm of our parameter vector, which effectively combines our likelihood with a circular prior model. So if you go for this, the posterior would look like an ellipse. So it's a classical linear analysis. The maximum a posteriori solution will be given by 0.2 and 0.3. So we'll have two components in here. The solution is clearly not sparse, and it doesn't even satisfy the original model. So we actually find a solution with an error. At the same time, if we do the same analysis but use a student t prior, what we find out is that the posterior looks significantly different. We already see that mass is concentrated on the axis. We do find a solution that is sparse, so there's only one component that is non-zero, and we satisfy equation exactly. So it's actually a solution that is sparse. So that gives us a little bit of hope that we will be able to find sources sufficient. All right, so now we know how to model all the terms in our PDE. So we want to identify the posterior of sources, concentration, wind, and hyperparameters given our measurement, which we can then combine as a essentially as a product of the model fit, which is our actual measurement likelihood. Sorry, the likelihood of wind and the concentration values. We have our PDE models that describes the dynamics of the process. We have our priors that determine the prior information about the wind and the sources, and we also have a hyperprior to enforce sparsity over the source distribution. So how do we typically approach that? Well, this is a classical case of hidden Markov model representation of a dynamical system. So that's we just have a few parameters. These models typically start with some initial conditions, and then we bring all these parameters into relationship. So for the step one, we see how our measurements are related to concentration at the time point n, and the wind at time point 1, also the sources given the sparse pi gamma, and then we can propagate this hidden Markov model over time. And the question is, of course, well, now we have a pretty complicated graphical model that describes the relationship between these variables. What do we do with that? And the approach that there are a number of ways how you can approach inference on such graphs. An approach that we have used is essentially an analytical approximative approach, where this hidden Markov model is represented using factor graphs. So what are the factor graphs? Essentially, the factor graphs are bipartite representation, bipartite graphs that make use of the factorization of our joint PDF. Sorry, that's a joint that has to be a posterior PDF. Sorry. So they make use of the fact that our posterior PDF can be factorized, and this factorized representation can be captured with two types of nodes. The circular nodes are the variables of interest, so that the circular nodes that you also see here, but the relationships are represented by the factors, and these factors are essentially on the graph. You can see them as square nodes, and these factors represent functional relationship between variables in our graph. So what you see here is actually a sampled graphical representation of a single element in our graph. So this is a concentration at a single element FC, and their relationship with other elements are neighboring cells. So these are the cells that are spatially located close to a particular cell of interest. So that's a concentration at a certain element. These circles, I don't know if you can see my my pointer. Do you see a pointer here?
We see the mouse, yeah.
Okay. So the circles here, I'm sorry. So the points here, the circles here, represent the spatially neighboring cells. And you can also see the temporal relationship, so the dependency on the previous concentration value times step n-1. So that's just a single snapshot from this graph. But the advantage of that is this factor graph can be used to derive efficient inference algorithm on such graphs. So you can use a number of algorithms. For example, quite popular are some product or loopy belief propagation methods, which essentially operates by transmitting messages between factor nodes to variable nodes, and from variables nodes to factor nodes in more or less a random fashion. So you send messages until a certain convergence criteria is established. And by doing so, by propagating multiple of these messages, once you converge, at every node, you come up with a representation of a marginalized density. So at the end of this update cycle, every variable node has or stores a marginal PDF of its value. So even if it is not observed, of course, that's the main reason of the inference, is actually to obtain these representations. Of course, what you see, as I said, is just a single cell. For a single moment of time, what you have is a graph that you see here. So it's a pretty complex graph, and as you can imagine, this graph also repeats in time for every time step. So you have to recreate this graph for every moment of time, which turns out to be a pretty complex structure and quite computationally demanding. And this is where the swarms actually can be used to simplify computations, because what you can do, you can actually cut this graph into separate portions and make sure that the information is allowed to flow between these different portions of the graph. And then you can put portion of the graph on an individual drone. So you, of course, need to, or individual robot, you need to make sure that it has some computing power. So you would need a certain computer on the drone and a communication link to ensure that between the computations done over this block, you can transmit data to your neighbors. And in this way, you can actually simplify computation sufficiently, quite significantly, because instead of doing everything on one processor, you can actually split it over multiple robots. An additional advantage of this approach is that you gain redundancy. So if one of the drones dies for whatever reasons, at the next time step, you can recreate or repartition the graph in a slightly different way. And then the swarm with fewer drones can essentially overtake some of the computational some of the computations, and the whole system can actually perform further. In this way, you can also make sure that measurements are done at different locations in space, and you can devise more efficient coordination algorithms. So let me just give you a little bit of a taste how such algorithms work. So for simplicity, we would assume a static diffusion equation, which implies that there is no time difference. So it's kind of you can think of it as a saturated state when there is no longer change in the concentration value over space. So the discretized version is then very simple. So it's just a simple equation without time change and so-called Dirichlet boundary conditions. So the concentration at the borders is 0. So we assume a mesh with roughly 500 nodes. So that you get a little bit of understanding what are the dimensions involved here. So, for example, the diffusion, the matrix D that is corresponding for the diffusion term, that would have 500 times 500 entries. The boundary condition with 85 nodes on the boundary would be then 85 times 500. And we take 500 random measurements. And this is the result that you would obtain. So you would obtain then from these 100 measurements, you would obtain a map of the gas concentration, and you would obtain also a solution for the source distribution that is sparse. So you see there are only 2 sources that coincide with the locations of the true sources, and you can see where the measurements were done. So the stars here represent the measurements locations, and in this particular case, it's of course random. It turns out that the random measurement strategy does lead to an acceptable estimate, but at the same time, it's not as good. So the exploration strategy, random exploration strategy, is probably not what we want. And as I said, what we really want is actually to find how the information is distributed through the space. We want to find effectively a distribution of the uncertainty or the information about the process of interest, which we can actually derive from the posterior or marginal distribution, and then navigate our robots to the locations where this uncertainty is high. So that's what we use as the proposal for guiding our robotic system. And using our factor graph representation, it turns out to be actually quite simple. So we do our standard inference, which give us an estimation of the source and the concentration distribution. And at every cell, we of course also obtain the value of the certainty, because our inference give us also the PDFs, the marginal PDFs of the variables of interest. And this is what we used as optimization criteria for our exploration. So we can measure uncertainty at those locations and go there where the uncertainty is higher. So that's what we use. Clearly, this measurement location can be selected by multiple robots. So we typically need also to solve the problem of coordination. So when the robots are driving towards the location of interest, the question is, how does it resolve conflicts? And there are conflicts. We follow actually 2 quite simple strategies. So one is called replanning, which essentially implies that whenever we have a conflict, we just select a different point from a pool of possible points of interest, because we have our uncertainty map, so which can just select maybe a second best point, or we can do evading strategy, which implies that there is a certain priorities between the agents, and the agent with a higher priority gets to follow his point. The agents with lower priority either have to replan or wait, depending on how the system is implemented. Again, that's a little bit suboptimal strategy, but it works practically. So let us now look a little bit at the experimental results. So as usually we start with simulations. So what I will first would like to show you is what happens when we do not make use of the sparsity assumption about our sources. So what we will have, so what we see here is a ground truth concentration with the wind that goes essentially from lower left corner to the upper right corner, and we have two sources. Again, the robots do not know how many sources we have or where they are. And we'll consider two cases. So one is uninformed case, so there is no prior information about the sparsity, and informed case where we assume that the source distribution is sparse. The first iteration after 10 measurements, we see that the informed robot would actually take measurements along the plume, which is already quite a good sign. The uninformed robot actually would take measurements everywhere. And of course, you would see that the estimation of the source distribution has not yet converged. So we don't have enough measurements to estimate. But as the time proceeds, so after 30 measurements, the informed robot actually gets much closer to the ground truth concentration map and is already able to identify the first source quite accurately. When uninformed robot still actually makes a lot of errors and the estimation of the concentration is also not so good. After 50 measurements, the informed robot gets very close to the concentration map distribution and it was able to identify the correct locations and the number of sources. Uninformed robot continues to sample basically uniformly through the space and requires significantly more measurements to be able to estimate the sources. And again, the estimation of the sources is not as good as compared to uninformed robot. If we look at multiple simulations, we see that the use of the sparse prior, so the red curve, actually is significantly more efficient in terms of NMSE, as well as in terms of the so-called Earth movers distance. So essentially, when we compare how well the sparsity patterns of our signals are estimated, and in both measures, the informed robots perform significantly more efficiently. So we are much faster in identifying both the concentration as well as the sources, as well as the source distribution. The next step would, of course, be to go to the robots, and what you see here is a small experiment which we call a hardware in the loop experiment. So the robots are real, the data processing on the robots is real, but the gas is artificial. So they take synthetic measurements of the simulated gas process in the small environment, and as you can see, the estimated gas concentration is actually quite accurate. And after a certain number of measurements, also the number and location of the sources is estimated correctly. We also redone this experiment in a real world with real gas sensors. Here we used alcohol as a toy gas for experiments. So you see the measurements with real gas sensors are not that fast. So the robot needs some time actually to acquire the accurate concentration. And that's actually one of the disadvantages of using chemical sensors, for example, in comparison to using cameras, because these sensors do not provide you the same rate of information about the process of interest. So this prior is extremely important. As a source, as I said, we use here ethanol vapor, which we kind of artificially excite in order to create sufficient gas concentration. And the robot has been then essentially customly built by us. It was a small Raspberry Pi for data processing. And on the same Raspberry Pi is actually, we use a numerical algorithm to, and a message passing. And interestingly, using this data distribution and processing approach that I have described before, we were able to solve this equation in real time. So thanks to this essentially partitioning the complex graph over multiple robots, the computations were done in real time, and the robots were able to to estimate the next waypoint and the concentration in real time. And as a source, in order to kind of excite the gas, we use here a small fan array just to make sure that the gas propagates through the room. If you look now at the result of this experiment, so after 1 minute, that's a kind of a concentration that we compute. As you see, the number of sources is not yet accurate. The concentration of the gas approaches what we suspect is actually the real one. And after a certain number of measurements, or roughly 11 minutes, we are able to identify exactly 2 gas sources, although the localization is a bit less accurate here. So there is a certain error in location, but the number of sources is essentially correct. Of course, our next goal, and that's where we are right now, is to go into field and repeat these experiments with real gas and with real robots, which brings new problems. So far we have tried, again, ethanol, we tried ammoniac and smoke grenades to create these gas sources. There we need to measure wind more accurately, but also other problems arise. So we realize that, of course, let's say the world in the lab and in simulation is not as good as it is in reality. For example, what you see here is the measurements that the sensors provide. So you see the measurement are not continuous. So we do not see the continuous stream of concentration measurements. So we only get measurements when we are in the plume, and the gas plume is not as nice as we have seen in simulation. So it's actually quite patchy. The wind has an extreme impact on that. And from what you see here is the trajectories that the drone has flown, and there are only 5 measurements. And from these 5 measurements that we were able to collect something, although the number of measurements that we collected is higher, but the measurements where we were able to see something is actually quite small. So we were able to identify the location of the source, but it's still not ideal. And we need to also modify our measurement model to take into account that we do not always see the concentration at a location. So that needs to be taken into account. And that, of course, creates a number of problems, practical problems, and this is where we are right now. So for the sake of time, I would actually skip. I also have a few slides about airflow exploration, because that's actually where we started to look at a more complex model for wind modeling. But I would just maybe skip over this a bit. So I think that these are nice slides. So we also repeat this experiment in our laboratory. We use 2 robots to actually explore in a similar fashion the wind field. What you can see here are, for example, the estimation in real time of this wind field, which we actually pose as an exploration problem. So we, again, using this information driven criteria, try to identify what are the best locations to measure the wind, so that we can see the airflow more accurately. And that, of course, required into, again, predicting more accurately the distribution of the gas. So let me now jump to the last slide in my talk, a little bit in conclusion and outlook. So I hope you were able to see that the problem we are addressing is quite multidisciplinary. So we need to have some knowledge in numerics and analysis of partial differential equation. The machine learning tools, for example, sparsity, plays a significant role in making these models more realistic. We need, of course, a lot of robotic aspects in order to bring the simulations into the practice. What we also saw is that, for example, using this physics-inspired modeling actually helps a lot, especially in situations where your sensor does not provide you sufficient information about the process. So I mentioned a couple of times this a chemical sensor provides you essentially a point-like measurement in one point in space and time, while your process is actually quite fast. So you need to kind of compensate that. And this physics inspired or physics-based prior or knowledge supports modeling quite a bit. What we also saw is that probabilistic approach towards the inference is actually quite fruitful. So first of all, efficient inference schemes can be constructed. And second, it also provides a basis for designing information-driven exploration strategies that performs very well, both in simulations as well as in experiments. But as usual, quite a number of open questions remain. In particular, we saw that when we make measurements with drones, then we perturb the process we measure. And then, of course, the question is to what extent or how strongly we perturb this process. Can we neglect it, or how to take this into account? Another aspect that are actually quite high on our agenda right now is how to capture some of these effects, in particular, some of these nonlinear effects like turbulence that are very complex to model using machine learning tools that would allow us essentially in experiments to have systems that are real time, that are efficient, despite the complexities of the numerics involved. All right, so this is where I would put a point in my presentation. Thank you very much for your time. And if you have questions, please ask. I'm here to answer them.
Yeah, thank you very much. That was a very inspiring talk. I like the interdisciplinary here. Since I have to leave in 3 minutes, I would like to ask Erich to moderate the question and answer session from now on.
Okay, thank you, Oliver. And thank you, Dmitriy Shutin, for this very, very nice talk. It's a holistic approach, I would say, to this gas concentration approach. It's very, very, very inspiring to see all the concepts that work together to get actually something done in the real world.
Good, thank you.
So with that, I would like the audience to ask the audience if there are any questions. So please either raise your hand or unmute yourself.
I can maybe ask a first question before I leave with hopefully a quick answer. When you think about carrying out these experiments in the field, as a glider pilot, I know that wind is very complicated. So it changes speed and direction over altitude. It's influenced by thermals. It's influenced by obstacles and relief and things like that. So even if you use wind priors from weather models that are certainly not resolved highly enough to deal with local situations, how realistic is it in practice that this will work?
Yeah, so that's this is a very good question, and this is actually what we also observed. So we started with this weather forecast prior, so very general priors, quite conservative in the beginning. Then we quickly realized that this is not, let's say, the proper way to go. And this is essentially part of the slides that I have skipped. So we realized that we need to measure the instantaneous representation of the wind. So we need to know it more accurately. And so we need to explore the wind field as well. And you can approach the exploration of the wind field just as we approach the exploration of the gas concentration. So you can come up with, we know that the wind dynamics is modeled, can be modeled by Navier-Stokes equations. They are nonlinear, quite complicated, but nonetheless, they can be represented in a similar fashion. So you get, you can discretize them. So you can design a probabilistic approach to infer parameters of these equations. And then you can design robots to take samples of these of the wind concentration, and these measurements are used then to compute the wind field and insert this estimated wind field into the inference problem for gas concentration. So you can actually glue these two exploration problems together, and you can glue them actually quite efficiently because both are described probabilistically. So effectively, you use a graphical representation or probabilistic graphical models to glue them together. So they are really tightly coupled. And then estimation of the wind is then directly influences the estimation of the gas concentration. And these are estimations that are instantaneous.
But I guess you would need dense samples in 3D, in a 3D volume, right?
Of course, yes, sure, of course. So what I have shown is 2D, a bit simplified, but the models that we use, they are, of course, they're in 3D measurements, yes. And there a number of robotic problems apply. So how do you make measurements in 3D efficiently, avoiding obstacles? So there is, yeah, as I said, a number of open questions still remains.
Okay, thank you. That answers my question. I need to leave, but you are, of course, free to answer more questions, and Erich will take over from now. Thank you very much, Dmitriy.
Yeah, thank you, Oliver, for invitation. Yeah, thank you.
See you later.
See you.
Maybe one follow-up question directly. Actually, I think it's a 4-dimensional problem because you always have time also in it.
This is true. Yes, that doesn't make life easier, although the time is somehow inherently encoded in the model. So although we do sometimes make a simplification by assuming that the situation is stationary, and as an example that I show here is actually a stationary Navier-Stokes equation. So we ignore, here the temporal change. So we assume that the wind is stationary.
Okay.
Yeah, that's a simplifying assumption. So that's where what we typically do as a first step, just to understand how to deal with these quantities, to develop the mathematics and understanding of the quantities we are dealing with. Because at the end of the day, we are engineers, not mathematicians, so we need a bit more time to understand how to approach these equations and solve them efficiently. But after some time, the time plays, of course, a very important role. And the time is a fourth dimension in this respect. This is true.
So maybe I don't know if I had one question regarding your chart. It was around 21 or 22, because there the assumption essentially is that the wind, there's no temporal dependency between the wind. Yeah. Model that was resolved, I guess, when you estimate also the wind.
Yes. I know what you're talking about. This is
the previous time step is a good prior for the next time step if the temporal evidence is quite high.
Yeah. So let me scroll back to the slide. So that has to be here. Yeah. Again, that's as we find out, that's a very unrealistic assumption. Yeah. So it works well in simulation. So as you can see here, the wind is just basically a uniform vector field over the exploration area. This doesn't hold in practice. That makes life easier for the inference, but that's an unrealistic model. And this is where we started to think a little bit more about what are the realistic approaches to modeling wind. We know in the literature, people, for example, were using Gaussian processes to introduce a little bit of diversity into the wind distribution. That's one of the approach you can proceed. So one can again say that X and Y components are independent and you model them independently, or you even incorporate some dependencies between them. You can do modeling in Cartesian coordinates, or you can model wind direction and wind speed separately, using, for example, for direction von Mises distribution and for direction Weibull distribution. So there are actually quite a number of statistical models already available for wind modeling that we borrow from weather forecasts, weather scientists. So there are a number of models that already exist. But for our purposes, we realize that we need, again, a more informative approach. So we need to know what happens exactly at this location at this moment of time. So this model with weather forecast can still be used later, because you can still use it as a prior.
Yes, of course. Yeah.
But
it's a prior in this form, right?
Yes. But in certain way, you need to measure the wind in the field and incorporate the measurements of the wind into the estimation. And since we use a Bayesian approach, let me jump to the slides with the network. So essentially, since we follow this graphical model approach, so what we do, we just extend the graph. So we add to this variable, we add additional measurements. So here you see the measurements of the wind, and you can extend it. So you can have a model here that describes, for example, the dynamics of the wind. So on the slide that I skipped, we use incompressible Navier-Stokes equation to describe wind flow, and we use individual wind measurements to effectively interpolate over the space. So the model is used kind of to fill the gaps between our measurements position. And of course, since this is done in a probabilistic way, you can still incorporate your weather forecast.
Yeah, that's the nice property of Bayes, actually, of these graphical models, actually.
Yeah, exactly, yeah.
So, and yeah, the mixing coefficients, so the parameters of all your models, you essentially determined by belief propagation.
Yes, or in this case, loopy belief. Yes.
Yeah, loopy belief. Yeah, okay.
which is of course can be considered as yeah, it's I mean a mathematician would tell me that's not an algorithm. It no one knows whether it converges or not, how it performs. So forget it. That's not an algorithm. But as an engineer, we actually do testing and see that it converges and its solution makes sense. So we use it. Yeah. But we get so face laps from mathematicians from time to time.
Yes, I totally understand that. So before I ask a follow-up question, maybe somebody else from the audience has a question regarding the talk. So feel free, please. Oh, there's something in the chat. I've missed it. Okay, those were goodbye sentences. Okay, because now I would like to ask, coming more to a practical point of view, you said that you compute everything on Raspberry Pis in your hardware in the loop experiment. How complicated are these meshes then? So how many nodes can you compute on the?
Very good question. Very practical question, I would say, and it very much depends on the discretization domain. So for experiments in the lab, so you essentially what you can see here is a kind of a discrete representation of the exploration domain. Yeah. So every cell here is kind of a small portion of the graph. So if you have more, if your discretization is finer, then the graph grows and becomes quite large. Exactly. If you have a three-dimensional graph, it actually grows. Yeah, it's a cube then, rather than the. And
dimensionality.
Correct. And for the lab experiments, we found that the Raspberry Pi was sufficient. But already for 3D, that's probably not the case. So, for example, for the drones, we use Intel NUC, which is a bit more powerful than Raspberry Pi. And it also very much depends on the scale on which you want to resolve the features. So we are talking about the dimensions of roughly, I would say, up to 100 times 100 times 100. So it's a cube. We think about maybe a small facility or gas storage appliance or a storage facility. So the dimensions are relatively small. And we say if we can localize the source up to, let's say, 5-meter accuracy, that's sufficient. So our cell size in this case would be 5 meters, 5 times 5 times 5. So that's still relatively manageable, but might be not enough for Raspberry Pi. And what I haven't shown here is the advantage of this Raspberry Pi, of this factor graph approach towards inference is the fact that the messages are essentially relatively well defined. So it's not the kind of classical particle filter based solution, rather than it's analytical approximation. So the messages approximate the densities. and they're computed analytically. So essentially what you exchange as a mean and variances, so it's a kind of a Gaussian belief propagation. So they're quite efficient and the messages are the same. So we thought, well, maybe we can speed it up a little bit if we do it not on a computer, but on FPGA. And we had a paper published recently on that, which essentially an FPGA solver that can solve such equations, provide solution to a partial differential equation in our setting on a chip, and that's very efficient.
Yeah, the belief propagation is actually a very efficient algorithm. So you only have to accumulate, marginalize, and multiply. So
yes, and you have to do it for essentially you do the same operations for multiple nodes, and that's what FPGA is actually quite well at doing.
Yeah. Maybe one thing, but I'm also coming from TU Graz, and that was in Tom Pock's group, so we were doing always a lot of computing on GPU, where you have also this massive amount of parallel computing. So belief propagation is especially suited for that.
Yeah, that's another reason why we like it.
And maybe one point, have you also, since you have an underlying model, a physical model, so this PG, have you also considered coarse to fine approaches? So where you start with a coarse approximation, discretization, and then refine it based on your measurements. And
yeah, we thought about that. Yeah, that's correct. So you can actually do mesh refining. Yeah. And there are approaches to deal with that. We are aware, but I have to say we haven't tried that yet. But it might be interesting because in areas where you do not have sources, you do not require a high mesh refinement. So at the borders of the domain, there is no need to have an kind of a very accurate mesh distribution. It actually might be important for the wind. Especially around the obstacles. So this last simulation that I have shown on the last slide, where we look how the wind propagates through the obstacle. So there it might be important because so you could see here this a 2D case actually. In 3D case, it's important to know how the wind actually goes around buildings, because that's where we want to go. We want to have an experiment and a certain facility where you have structures, and they of course created a very local wind phenomena. And to know how the wind looks at those locations is particularly important, because the kind of the vision that we have for the system is visualization of these 3D distributions for firefighters or for disaster relief personnel, because you can make this invisible gas visible through augmented reality or virtual reality devices. And in particular, in, let's say, close to the buildings, you would like to identify maybe areas that are particularly affected or where the concentration are particularly high, or areas where the concentration is particularly low, which you can then use to, I don't know, save people or accommodate people during disaster or whatever. So that you can have this visual representation, and obstacles play a very important role. And this is where you could actually refine the grid.
Yeah, that's promising. It's actually related to also your uncertainty estimation, because I guess you also have a high uncertainty in these areas.
This is this is not necessarily so. The distribution of the uncertainty depends very much on a particular value of the function that you observe. So, for example, what you see here, this is an uncertainty. This is a wind exploration. So you have here two obstacles, and the wind, actually, you have a fan here. So that's kind of a ground truth. So that's a fan on one side and the fan on the other side. And actually what the system tells you is that you have to measure first at the corners. So you need to know the boundary of your domain, which kind of makes sense. So if you think about that you're in an open space, you have somewhere, so we do not assume walls here. So you have an open space, so the material can flow freely, and you have two fans, and you want to know how the wind is distributed. So essentially what you need to do, you have to kind of go to the borders of your space and look how the wind is there. And that's what the algorithm tells you. So it doesn't tell you that you need to measure at the obstacles. It actually knows pretty well. So if the fans are here, you won't see anything on this side. So that's kind of built into the algorithm, into the system. So it knows that borders are more important than obstacles.
So in this simulation, the obstacles were known in the model.
Yeah. We assume that the
boundary condition that there's zero wind in the model, in the obstacles.
Yeah. So we say that the borders, so the boundary of the area is open, so the air can flow out, but the obstacles are concrete, so the air cannot flow in.
Okay, I see.
And
if you remove that information, I would assume it would.
Oh yeah. Of course, yeah. If you don't know that, that of course would change the boundary conditions. Yeah. So here the boundary is unknown. We just know that the air can flow through the boundary. That's what we built as a boundary condition. But the values of the wind at those locations are not known. And so we say that it can flow, but we do not constrain. It's not a Dirichlet boundary condition. So we do not say what is the concentration at the border, or in this particular case, the wind field.
Boundary, probably.
Yes, exactly. Yeah. And but for example, for the obstacles, we say it's actually Dirichlet, so it's zero.
Okay, yeah,
so it can flow through. So the algorithm tells you don't have to measure close to the obstacles.
Okay.
You have to first start measuring at the boundary.
Okay.
And this is something that we actually didn't know. We were quite surprised actually to see that when we have a wind, that this infotaxis approach tells us that we have to measure upwind. So we have to go to the in the direction of the wind. And that was actually quite surprising. That I found really interesting. That it has.
Isn't it a consequence of the boundary condition and also the Gaussian prior? Because when I look at the exploration criterion, you see everywhere where there is some knowledge, there is a small blob around with some variance.
I guess in some sense, of course. I mean, that's kind of the result of this prior modeling, yeah. But we never said that it should start measuring upwind, yeah. And this was surprising. So of course we have the prior and we have the model itself, but the uncertainty distribution before we observe the data already tells us we should measure upwind.
Yeah, but maybe one.
Oh, sorry, upwind or downwind. So we have to stay exactly we have to stay in the wind. Yes, and this was surprising, because if we compare this with a non-informative approach, it just measures everywhere. So this assumption of sparsity and the wind told us, do not measure everywhere. Go into the plume.
But if you consider maybe one last question from my side, then it's.
Of course, yeah, sure.
Because you have this modeling that you have a Dirichlet boundary condition at the obstacles, so they pull you down in the uncertainty.
Yes.
And on the boundary you have von Neumann conditions, so they maintain the level essentially, right? So you will always have an increase towards the boundary.
Of the uncertainty, you mean?
Yes.
If you have Neumann conditions,
when you look at the initial time step, so
yeah. Yes, you would, which is maybe also not that surprising. So you would say, okay, I do not know the boundary. Let's first find out what happens on the boundary, and then discuss what happens inside the area. Yeah, that's possible. I don't know, maybe that's a kind of a trivial result of this modeling. But nonetheless, that's the result. That's what we see. So we do need to know what happens at the boundary. In particular case, what concerns the wind exploration.
Yeah,
With the concentration, it might be a bit different. Yes.
Okay, so I would have actually more questions, but I think to the sake of time, I'll once give every other participant the opportunity to ask questions. So please raise your hand. Okay, so I guess there are no further questions. I once again would like to express my gratitude for this very nice and inspiring talk.
You're welcome.
Thank you very much. And yeah, I would like to close this invited talk then. Thank you very much.
All right. Thank you, Eric. Thank you all for inviting me. It's been a pleasure. Yeah. Thank you. Good.
Yeah.
Then bye-bye and have a nice day.
You too. Bye.
Bye.